Hi everyone. So today we begin today's lecture. Today is April 27th, on Monday. So today we're not going to learn new material. What we're trying to do is basically we're talking about some information about the final. Okay. So final is going to be on Monday, May 11th, as scheduled before. So it's going to be an open book test, time limited. So 9 a.m. to 12:30, okay, p.m. So 3 hours and 30 minutes, and you need to upload your test by 1 p.m. as usual. Okay, so what we're trying to do is I'm going to tell you some how do you prepare for the final. Okay, for this. But some of the we are going to have more information later probably. Okay, now first. So the final is going to be focusing on the new material only. All right. So let me say that let's talk about the everything which is not covered by the previous midterm will be covered by the final. All right. So about homework. So actually we have a number of homework we signed on chapter 8, which is not covered by the previous test. So if you look at page 144, okay, you can talk about, pay attention to the number 14 and 15. So this is the Riemann, Lebesgue lemma, right? So actually, and we give a detailed proof of these things in the first remote lecture, and we have done this months ago. So this is an important thing for you to review. Okay, so we are going to test about this Riemann-Lebesgue lemma in the final, and also you have to pay attention to number 17 and 18. So these are the things about the L2 space and also the Hilbert space. So this is something you have to pay attention to. Okay, also important. So beside this, so this is still in chapter. So these things, okay. So these things, all about chapter 8, the LP space things. Okay, but we also talk about the solid space, and solid space is another important thing. We actually planned it at the very beginning of this semester, which is also going to be covered by final. So of course I'm going to now talk about the other part, right? And so let's look at the solid space part. So today's lecture will be short. So on Monday I'm going to have a Zoom meeting with you. So if you have questions, we can talk more about it, right? So for the solid space. For solid space. And of course, the most important thing is the concept, right? So you have to talk about the concept. So a different kind of solid space. And actually we begin with the first dimensional case, and then we talk about multi-dimensional case. So the notation WKP and omega. Omega is going to be a domain in the n-dimensional space. So you have to understand what exactly how the space is defined. Okay, this is important. And how this space is when we consider as a Banach space, and how the norm is defined, and also the equivalent norm things, right? But also, so there's another thing we haven't covered yet. It's WKP, and there's a 0 here. So we're going to talk about this on this Wednesday. Okay, the Wednesday lecture is going to talk about this. All right, so this is a basic concept, and so there are some homework I assigned and during my lecture, and you have to be put into your review list and prepare for the final. So there's a couple of things. So like say the completeness of WKP. So how do you prove completeness? We have a very standard way to prove it, right? So this completeness of WKP space is based on what? It's basically based on the completeness of the LP space. Okay, so this is an important thing you have to practice for some examples. And in the final exam, I'm going to probably I'll take a special case and ask you to give a proof of the completeness. Okay. Now, when you give a proof of completeness, you're not supposed to just copy or remember the general proof. You have to apply this idea to specifically to the case in which I'm asking you to provide the proof. All right. So it's very important for you to understand the meaning of this proof. Okay. Another thing is let's see, the relationship between weak derivatives of the weak derivative. And remember, we talked about this slide before. So in the weak sense, this is still hold like this. As triple derivative, you put another second derivative. So I mean, you take this triple derivative for f first, and you take the second derivative. Okay, so this is supposed to be equals to f5, right? The fifth derivative. So obviously we know this is true in the strong case, but in the weakly, in the weak derivative case, this is still true. If you assume that f is in the Sobolev space, okay, higher order Sobolev space, this is still true. So I want you to also understand this. I mean, look at this proof. I created a similar proof before in the test. Now in the lecture, right? You also need to look at the multi-dimensional case. It will go like this, like f alpha. Oh no. So you have the d. The d stands for the derivative, right? So d. So if I so d alpha. Yeah. Now alpha is a multi-index, okay? So that means you're taking the partial derivative, a mixed type partial derivative for f, okay, in the weak sense, okay? And then you take another partial derivative in the weak sense with beta. And this is supposed to be equals to d alpha plus beta. It's just the alpha plus beta. And f. Yeah. Now if f is belongs to WKP omega, and suppose alpha plus beta, the norm, is less or equal to k. Now as long as this is true, then you are going to have this relationship. So weak derivative relationship. So this is also important, and maybe some example I want you to prove in the test. And another thing is about the the existence of weak derivative. Weak derivative. So actually we see this example before, like suppose you have a domain like this. Either in one-dimensional case or multi-dimensional case, we talk about this again. Suppose you have some isolated singular point. So suppose that the function is actually differentiable over the entire domain except on this isolated point. And suppose the f is, for instance, the derivative is bounded. Then you can see that the strong derivative is actually the weak derivative, even though the strong derivative are not defined on these isolated points. And also in the last discussion, we also mentioned that and this point may not be really discrete point, isolated. These point maybe can have some accumulated point. Okay, for instance, like so these points will be accumulated somewhere. So now as long as those points can be covered by small circles, a finite number of small circles, and then you can show that the strong derivative without this point is actually the weak derivative. And you can review the example we talked about this last time. In the 1D case, and also the multi-dimensional. The multi-dimensional case, they all works, okay? So these are the things you have to try to prepare. Now another thing, we haven't talked about this yet, but we're going to talk about this on Wednesday, is the Pointillés inequality. Okay, so this is a very important quality. So in the solid space, there's a couple of important qualities, and Pointillés inequality is a very important one. And you have also the embedding theorem in those solid inequalities. So we're unable to, in this class, we don't have much time. So we're not going to cover all these inequalities, but at least we can cover the Pointillés inequality. It is very important. And this one should also be, the proof of this one is also important. You should remember, okay? Maybe I will ask you to prove a special case during the final exam. Okay, so pay attention to this on Wednesday, and about this inequalities. And basically this inequality is related to W0 KP space. So we want to define this kind of space first, okay? And then you can talk about the Pointillés inequality. So this basically all the things I'm going to cover in the finals, okay? And tomorrow during the lecture, in the Zoom meeting, and if you have questions, we can talk more about this, okay? So I just want to stop here, and then we're going to continue on Wednesday. Wednesday lecture is going to be defined as W0 KP space. All right.